So, previous class we were studying about dipymethane rearrangement. We just saw like how we can do dipymethane rearrangement, and we studied the another class of dipymethane rearrangement, that is oxa dipymethane rearrangement. And I slightly introduced the aza dipymethane rearrangement. Okay, so this class we will talk little bit more about aza dipymethane rearrangement, and then we will move to PhotoRearrangement of other compounds, right. So, we will start with aza dipymethane rearrangement. So, I have explained you that if you have a system like this, and if you photolyze, you end up type of 1,4 diradical, right. So, we said that this can be, you can cleave this in both the ways. One, you can cleave this direction, so that we can call this A. Another way you can cleave around this way, so we can call it as B, fine. So, if we go in the direction of A, you get a system like this. When you go in the direction of B, then you will get so this what we studied in the previous class, right. So, you can in aza dipymethane rearrangement you can see both the products formation. Okay. So, now what we will do is that we will try to do some examples on this aza dipymethane rearrangement. You take this compound, and if you photolyze this, what do you expect? You can think of this should be straight molecule. So, you can have a 2 radical system like this, right. So, now which will be better to cleave on? You have this direction, you can cleave A or B, right. Which you like to cleave? You have a choice of cleaving A, you have a choice of cleaving B. Which you want to do, direction A or B? See, if you are going to cleave this bond A, you are going to end up with a type of an alkene system across your cyclohexanone. If you are going to cleave B, then you are going to end up with a type of imine, right, and that imine can hydrolyze to give you a ketone if you do a column and everything. Okay. So, Is my carbon is less? No, no. 1, 2, 3, 4. 1, 2, yeah, 1 carbon is less, right? 1, 2, 3, 4. You get this product, then this bond, then 1, 1, 2, 3, 4, right? So, this bond cleaves around. So, you get here the cyclopropane. So, you have 1, 2, you have 3 and your nitrogen is here, okay. Then you can get, okay, sorry, you can get your OAC, right. And this imine can hydrolyze to give you ketone sometime, fine. So, I am breaking this bond, I am just making a cyclopropanation formation here and with my imine, clear. Okay. Now, the same type of another example which you guys can do. Same thing. What is this compound without this called? What is the base moiety called? This moiety? Without this? Huh? Fluorinone, right? So, this does nice dipymethane rearrangement, this particular. So, what product you can write? Just write directly the product. So, you get a, do you want me to write the product? Got it? So, what you do is that fine, then you can cleave this, which can give you this product. Because once you cleave this, it become like, then you can make a cyclopropanation here with your imine, fine. This is as a dipymethane rearrangement, fine. So, that's are the 3 types of dipymethane. One is your dipymethane rearrangement where you have a diene which is non-conjugated with a central sp3 carbon. Then you can extend it with an oxygen and you call them as an oxadipymethane where you have a carbonyl as well as an alkene. Then you go for your azadipysystem where you have a aza molecule C double bond N with your alkene. So, these are the 3 types of dipymethane rearrangement, fine. Okay. So, now we will go to some other type of important rearrangements, which is photorearrangement of cyclohexanone systems. So, if you take a cyclohexanone, like you can call as hexenone if you want hexenone, it is better hexenone, not hexanone, cyclohexanone, right? It is hexenone. So, if you take cyclohexanone and if you photolyze this, and this case it is the solvent plays a important role. Okay, if you photolyze in presence of tertiary butanol, you get a very nice rearrangement. This is very common PhotoRearrangement happens. Like your dipymethane rearrangement, this is also very common in photochemistry. You take a cyclohexanone system, you photolyze that in presence of tertiary butyl or in the solvent tertiary butanol, you get up this type of rearrangement. Fine. So, we will just see how the mechanism works on this. Okay. See what happens once you photolyze this particular compound. What excited stage it goes? Initially it should go S1, then you cannot see much chemistry from S1, right, because it is type of a alpha beta enone system, right, ketone system. It undergoes a nice intersystem crossing. So, you get this molecule, all right. So, what happens to this molecule? Any idea what it can do? This is in the triplet state. Any similar structure can I draw the stable form? Can I write like this? Right, I can write like this. No? Now tell me what you expect from this molecule. What you can expect? See, you know the product. Okay, so my question is not like so. So you know what product you are getting. So it is easy to assume that what you are going to do. Yeah, what migration? 1, 2, 3, or you can, yeah, if you want to number from there, you can number, or you can say 1, 2, 3, 4, 5. Just for, I am not doing the proper IPAC. Okay, just for your thing. So what happens now? R migration, yeah, that is why I kept it R. If it is R is something like hydrogen or methyl, then you do not see much migration. Huh? Yeah, this C5C6 carbon, this shifts, it is a radical, shifts like this, okay, to give me O dot. Yeah, as you thought R migration is possible, okay, we should think what R we are looking for. Okay. See, it is a looks to be really nice migration, shift of your C5C6 carbon towards your C4 atom, and it's a radical, okay. then you can always create a radical here. So, you can combine this one. Right. So, when you do this reaction in the lab, then you feel how this process are so facile to happen. See, just this reaction does not take too much time. You have to take your compound, dissolve it in tertiary butanol, just photolize in a lamp, you end up with a nice product, okay, completely rearranged. Fine. So, we will see some good examples based on this photo rearrangement of cyclohexanone, which normally people ask in several exams. So, now in your stage what you have to do is that whenever you see a system of one member, like a single member, you try to do it for natural products in your stage, like MSc second year, or always you take it to the natural products. You have many good natural products in which you can do all this chemistry, extend to the higher member rings, okay. Do not sit with one member ring and do all the rearrangements. So, once I fertilize this, yes, now you know it goes to singlet, undergoes inter-system crossing, then you get a triplet. Then I can write, okay, I can write both the forms of this. Yes. Now what happens after this? What do you expect? Same, see, it's the same analogy which you are going to, because you are tried with cyclohexanone system, right, with a one member cyclohexanone. Now I am just using this. What happens there? Once you get a, say in this system, what happened? Once you get this, you get a shift, right? So why cannot you think the same way here? I can just shift this, right? That is why I said, like, when you do for natural, like higher members, it will be much more nicer understanding them. Right, just I have moved this, you get a nice thing. The stability can be assigned because this radical, it's again with a methyl, angular methyl, so that radical is stable. Now your final product, because this will become ketone now, and this radical will combine. Just draw the structure. See, this chemistries have been done like long before. You can think about how people have assigned the spectras. Now you are studying IR, NMR and all these things, right? You have that course. So, just see, you have no idea how it works. First you have to find out the product, then you isolate the product, then you assign their spectras. Any idea how you can differentiate this ketone and this ketone by IR? This starting material ketone, and how you want to differentiate these two ketones, not any which will be best way for you to differentiate? Huh? IR, how much it comes? This carbonyl. What is this carbonyl? This is an alpha beta enone. It's not just a carbonyl, right? Alpha beta enone, where it comes? 16? 1680 is ketone, 1720. So it is 1680. You are good. This one? Exactly 1720. That is cyclohexanone, right? What value? Where it comes? Yeah, see, yeah, when you are talking about IR of this specific, you should be little bit specific values you have to be. Okay, that is good. Then how you are going to say that this ring is formed? NMR, how you can say by NMR? See, this where the cyclopropane hydrogen comes? See, these are very specific values of cyclopropane. They are like much shielded, right? So you should get around less than 1. Like that you can easily identify. Where this alpha beta hydrogen comes, this double bond, they are also very specific if you see them. So that's how when you look a molecule, look in all the angles, just see like, yes, I am doing today PhotoRearrangement, but you can also see the spectra. It does not mean that the spectra which is taught in your class you have to just see that. You can see this molecules, they are very good for finding out spectroscopy, because one is cyclohexanone, another is cyclopentanone, and you are missing one double bond. Where this double bond comes? This hydrogen 6.5. This ketone in C13, still you have not taught C13, right? Yeah, okay. No, they have not taught C13. Okay. So please understand from this also. See this molecules, these are very good molecules to interpret your spectral values also. Okay. So same compound I have taken like a cyclohexanone system, but in this case I am specific with my substituent. Previously I was putting R, now I am putting phenyl. Okay. So what happens you will see. When you fertilize this, yes, you know it goes to singlet, triplet, all this intersystem crossing. Then you end up with your nice O dot, which will be have this. All right. Now what you expect? Shift of this. See, that's now what happens is that your shift of your phenyl becomes much more facile for it. The migratory aptitude of your phenyl is much more better. Okay, that's why the whole mechanism is similar. Okay, now you have to just check up the migratory aptitude. Now this becomes much more. So this undergoes a shift. You can call 1,2 phenyl shift. Okay. I get a radical here. Then I can just make this ketone and I can add this up, right. Yes. Yeah, this rearrange one. But if it is a phenyl system, you get. If it is a methyl system, yes, you will get it. Okay. But in the case of phenyl, they are very good to do 1,2 phenyl shift. Yeah, this you get. This you get in, if you see photochemistry, any photochemistry book, you can see this reaction. Now, if I take this if you consider instead of 2 phenyl, if I consider like an example, a system like this now with a cyano. Okay, the para portion is substituted by cyano. Okay. If I do the previous case, I was having 2 phenyl systems, right. In this case, I am taking 2 different phenyls. So, you know up to this, right. So, it undergoes a singlet, then intersystem, then equilibrium structure of this. Now, what do you think? Previous case, because since it was 2 phenyl, you were happy to move one of the phenyl. Now, these are 2 different phenyls. So, which because it is a radical chemistry, okay. Now, you have to think which phenyl you want to. One, you have a electron withdrawing substituent. So, which radical will be better stabilized, or which has a tendency to move towards this? This does not work like that. I think it is other way around. So, you get a nice you get this as your product. What happens? Why? And your bond also becomes weaker, na? Because it tries to withdraw all your electrons. So, among these 2 bonds, if you want to break, see, bond breakage is also important criteria. Then again your stability comes also. Na? This bond must be much more weaker if you see, because cyano wants to withdraw all its electron bags. Okay. And again then destabilize, then the stability comes. Then you have a nice migration. See, this you should know, right. So, you do not, most of the time you are not given with 2 phenyl systems, okay. You will be given with the systems with the electron withdrawing, and you have a system with an electron donating. Then you think about what happens, fine. If you have a chlorine and fluorine, I have that in assignment, I will give you that. If you have a chlorine and fluorine, I have phenyl with which has a chlorine substituent and another is fluorine substituent. Chlorine is any guess point? Anyhow, I will just give that in assignment so that you give me the product. Okay. And one more, this it's similar, but just I want to know that this also you should know the systems, because whenever you see this type of system, you are more try to do cope type of rearrangements. That is why I am just giving these examples. Okay. Like you can also think about photo rearrangement of cyclohexanone. This you know the product, you can directly write the product. What is the product? Which will be your shift, this methyl or this? Now you know very clear. Stability of a radical. Methyl shift. Why? Allylic radical is not stable. Yeah, allylic will be stable, no? So you can shift it, right? See, you want to cleave this, you get a methyl radical, another you cleave it, you get an allylic type of radical. Which radical molecule wants to cleave? Stable radicals, right? In this two, which is more stable radical? Come on, man. Allylic radicals are more stable, right? Yeah. Yeah, yeah. See, once it cleaves, it can move like this, ne? Right? You can always move your bonds, like which we are doing right now. Like this, you can move across. Ne? That I can do, right? So this is the product you got. Can move the bonds. If you want, you can do the other way around with a double bond here. That product is also formed. See, this methyl does not have, yeah, you will see sigmatropic shift where you have methyl, hydrogen and phenyl, but phenyl more has a very nice shifts towards. You can see methyl shifts, but I think it is more works in sigmatropic reactions where you can do. Fine. So, now what we will do is that we will go into, this is the basically photo rearrangements of your cyclohexanone systems. Okay. See, these are very important rearrangements in one sense, like if this photo rearrangements are like well known, like dipi methane rearrangement, photo rearrangement of your cyclohexanone system, any other rearrangement you can think about, which you think is you have studied in something in your bachelor's level also. What another rearrangement which comes in your mind? Any other? Yes, sir. Any compound which see there is photo rearrangement of dienones. Dienone systems, right there. This type of systems because this mechanism of the system is very important, where you can see some good concept came out of this. When you write the mechanism, you know that. What is the product when you photolyze this? Somewhat looks like dipymethane, okay, not exactly, but someone looks like a dipymethane or cyclohexanone reactions. See the product here, okay. So, yes, fine, we have a diene system, you photolyze, you get this rearranged product. You think this rearranged product can also undergo rearrangement? What is this product again? This is again a cyclohexanone system. So, this can again do the photorearrangement of cyclohexanone, fine. So, that is fine. So, we will see the mechanism. Mechanism is little bit interesting. This so, once you photolyze, you get this once, which is undergoing inter-system crossing to give my triplet. This you can pretty well write like this. This is again in the triplet state, right. What is this called as? Can you, what do you call this? Very rare example of an intermediate. Diene-Lec system. You call this an oxy-allyl biradical, very rare to see. Oxy-allyl biradical. You have seen allyl biradical systems. Okay. These are like oxy-allyl biradical system. See, when you are trying to investigate, there is group of research groups where they start working on understanding the reaction intermediates, right. For them, this type of radicals, their lifetime are much more interesting. So, this is oxy-allyl biradical system. Then what happens after this? What you can think about? Migration or simple bond formation, like your dipymethane rearrangement, right. I can just simply form a bond here with a phenyl. With this, just a bond formation, okay, with the radical here, that is all. This is in what state now? It is in triplet, fine. The whole chemistry is now working in triplet. Now, what happens, this particular compound, this is very nice, it undergoes again an inter-system crossing, very rare examples, undergoing an inter-system crossing from triplet to singlet. This is very hard to see molecules, most of the time you will be seeing molecules moving from singlet to triplet. Okay. This is a rare case where you can see a molecule moves from triplet to singlet. You can ask why. I will next step we will see why it is moving from triplet to singlet. Singlet. Now, I think those who have studied this type physical quantum chemistry lot or physical aspect of photochemistry, you have seen examples on spin orbital coupling, right, LJ coupling, you have studied a lot. What is that? Where the spin and orbital of your system come together, they couple, right. So, you can see that here. See, you can see this two electrons, okay, undergoes a nice spin orbital coupling. Okay. Once they undergoes a nice spin orbital coupling, you get a system like this, or you can say pi star to n d motion, people call them like that, or you can say spin orbital coupling. You can call them a spin orbital coupling, or you can call them as pi star to n d motion, different words of that, but it is a very good example to see spin orbital coupling, which tells you the story why it is important, because two radicals come and then becomes a type of deuterionic. Now, once you know this, then you can do this chemistry. Just a minute. Okay. You get this product, okay. Just a correction in your previous thing. You get this product, fine. If I take your previous example, I have to do some small correction there. This one, it's not this product, okay. This is more about you get this product. So, it is better, that is why it is better to write the mechanism and understand what product we are getting. So, you get this one. Both the same. Oh, fine, then it is okay. I have written in different way, then it is good. Okay. So, it is fine, because this is a very here you can think about oxyallyl biradical system, okay, one important thing. Then you can see about a intersystem crossing from triplet to singlet mechanism. Then you can see about spin orbital coupling. So, you have like new things in these mechanisms, okay, which is very important, that is why, fine, good. So, one more using this we can do one natural extra, just very famous natural chemistry, which you can see in the PhotoRearrangement. Same using this the PhotoRearrangement of enone system. See, I like to work most of the chemistry in natural products, because that sort of gives you lot of confidence. See, this you photolyze in the a system with little bit water, okay. You think like water is in this system with some organic solvent, because you do not dissolve this properly in water. You have water with little bit of organic solvent, you dissolve and carry out this photochemistry. So, what do you think? Yeah, you might end up, you get O dot, get this, then I can move across this one, fine. You can get a radical here, and get a nice system. Then what you want to do? Then you can make a bond here, right? R2, you can have a O dot, then you have a dot, you can make a nice bond here. R1, previous case, yeah, okay, R1, yes, thanks. So, I get an R1. Now, what happens? Now, you get your spin orbital coupling. You get a system like this. Yeah, up to this we are fine. Right? You get a. Now what happens? Yeah, this is your product. What happens if you have, because it's type of a deuterionic, right? Hmm? Cleavage of bond. So, I finished writing this. Cleavage of this bond. Or you think about like attack of some, because your solvent system has lot of water. So, can I write this structure? Now, you have your water molecule. It's the same structure, right? Okay, I'm just finished up. Yes, the same structure. Now you have water molecule. Okay, so this you have. I can attack here. Okay, pushing my system like this. Possible, right? I can cleave this bond. That will be the driving force. If I do that, what happens? Just write the product. What you can think of? Let's attack. I'm just breaking this bond. You get this? Oh, right. So you get a nice like 5-membered with your 6-membered one, and this it can undergo a sort of ketone. You can draw that. If you want, you can take other way around. It can undergo nice. You can get this type of system anyway around. That's fine. This, if I take other way around now, like again my water molecule comes and attacks here. Okay. Now, either in this case, see, one question you can ask always other way around. This we can, okay, you leave this, we will just finish up. Is this clear? Any doubt? Okay. Now, since it is an enone type of system and it is more like a different molecule, can you think about other way around happening chemistry? because you are exciting one type of double bond. Can you do in other direction and see what product you are getting? Can you try? Say you can think of making this one, stabilizing this side and creating a zwitterionic on other way around. Basically, you will end up with a system like this. Can you get this system if you do other way around? Okay, you will get this nice system now, because both of your dyeing systems are different in this case. So, you can take in other direction, you will get this now. Now, you have auto molecule. Now, you can think of doing what product you can get now. I can attack here, push my system, right. Then what is the product? Can you write? Just I am opening this bond. So, this one, just opening this bond, with R1, R2, five and 7. If you want to really draw properly, then you get a system. See, this is very good example in that dynamo system. That is why I said you take a molecule of, just do the photolysis, see on both the direction, try to do your zwitterionic formation of zwitterionic on both the sides and see what you get. These two products mainly when you do the photochemistry of this system, and if you see, they are very nice products, like you get a 5 with your 6 and other side you get 5 with your 7, very nice products. These are two major products you get when you do the photochemistry of this. Fine. Okay. So, that is about this part, rearrangements. I will take one more rearrangement, which is only for small, like for few minutes we will discuss, then we will stop. So, right now we will finish off, all right, in this class. Okay.